This is an application problem from chapter 2.3. It says the demand for a new computer game can be modeled by this function P of X. P of X is the price consumers will pay in dollars, and X is the number of games sold in thousands. And they're reminding us the definition of revenue here being the number of units sold times the price charged for those units, X, in this case, X times P of X. And then we got some questions to answer. So part A just wants us to find the revenue function. And revenue was defined as the number of units sold, which they told us was X. X is in thousands, and times the price. And the price was given as a function of X in that 46.5 minus 7 natural logs of X. So this should be the answer to part A. It's the revenue function. The marginal revenue function, well, marginal revenue is defined as the rate of change in revenue. We got revenue stated as a function of units sold. So marginal revenue here would be the amount of revenue earned per unit at any point of X we care about. So this is the derivative. The rate of change is always the derivative. That's why they have it notated as r prime of X. So we got to take the derivative of this here. It's a natural log function. It's got that ln x piece. And you could distribute the x into both terms and then differentiate them individually, or you could just go ahead and do the product rule because it's written as a product. You're going to need the product rule regardless of which way you do it to some effect. So I'm kind of inclined to just take the derivative in the with the form we have. So it's a product. We've got one factor here in x, and then this is a binomial factor because it's two terms, but we've got two things multiplying. So the product rule is suitable. So the derivative r prime of x using the product rule is the derivative of the first factor, which is just 1. The derivative of x is 1, times the second factor, this binomial factor 46.5 minus 7 ln x. So we got the derivative of the first factor times the second factor, and we put plus. Now we're going to do the derivative of the second factor, which is, we've got ln x itself, which you may recall that the derivative of the natural log of x with respect to that input x is 1 over x. So if we got a negative 7 out front as the coefficient, we could just call this negative 7 times 1 over x, or negative 7 over x. This is the derivative. Oh, and then the derivative of 46.5 is 0. This is a constant. So derivative of this being 0, the derivative of this term being negative 7 over x, we have 0 minus 7 over x as the derivative of our binomial factor here. So that's how we got negative 7 over x. So now we're going to multiply this times the first factor, which is just x. And then you can see that the looks like the x's are going to cancel as a factor of 1. So if we just want to simplify this derivative here, we're multiplying by 1, so that's just going to leave what we have here. We've got 46.5. This x's here are canceling, so we can actually combine our like terms. We got 46.5 minus 7, which I believe is 39.5. And then we just got the minus 7 ln x. And this is our derivative of the revenue function, which we can call the marginal revenue function, r prime of x. So we use the product rule for that. So just as a reminder, it turns out it doesn't even matter what order you follow, just because it's all the product rule is can be done in either order. But the way I did it was derivative of the first factor x, so that's this. Right, this is the derivative of x, times the second factor, which was that whole binomial factor here, plus the derivative of the second factor, which was the binomial factor. That was so we took a derivative of this, we got a 0, and then a minus 7 over x. So that's this piece. And then it's just times the first factor, which was the x. So there's our derivative. Now the last question, part C, wants us to determine the number of units sold. And if we were to read through the description again, or just recall that that was defined as x, x was the number of, it was thousands of units. sold. So we're going to be solving for X because that's the variable that represents what we care about here, how many units. And then they also give us a price. So probably, I guess the biggest challenge of this question is knowing where to put the 40 in. You don't want to use the revenue function because this is the money earned in revenue. It is not the price. So, and then for the same reason, we're not going to use the marginal revenue function either from Part B. We don't care about the rate of change in revenue relative to number of units sold if we're interested in plugging in a price of $40. So it turns out the function we want is actually given in the verbal description up here, where it tells us the price that the consumer will pay is a function here of X being the number of units sold. So we just got to make sure we plug this 40 into P of X and then solve for X. So 40 ends up being P of X, the price, and that is equal to 46.5 minus 7 natural log of X. And now we're looking to just solve for X. So we've got a logarithmic equation. It has 3 terms. Similar to an exponential equation, the first step would be to isolate the term that has the natural log piece. So we're going to get rid of that 46.5. If I subtract 46.5 here, I should get negative 6.5. So we're going to, what matters what I change here, I'll stick with the purple. So we're going to get negative 6.5 if we subtract that 46.5 from both sides. And then we've got negative 7 natural logs of X. And now to get that ln X piece itself isolated, I got to divide out that negative 7. So if I divide negative 7 or negative 6.5 by negative 7, I should get, let's see, I guess if I can double the 6.5 and double the 7. That's the easiest way to get that value. It should be negative 6. Or you could let the calculator do this as well. You could take the 6.5, divide by 7, right? Dividing by double negative is positive. So you can let the calculator get that fraction for you too, but just do a math, enter. So there's that 13/14. It's positive though, I don't know why I have a negative there. Okay, so now we've got this piece, and our last step is to rewrite this using its inverse. If you were solving an exponential equation, you would isolate the exponential piece and then write it as a logarithm. Here we're solving a logarithmic equation, so we're going to isolate the logarithmic piece and then rewrite it as an exponential one. So the exponential form of this logarithmic equation is, well, it's natural log, so it implies base e. The output of our logarithm is the exponent. So the exponent is 13/14. And then the input of our logarithm x is the output of this exponential statement. So to get this rewritten, it's base e, it's being raised to the 13/14, and then the output is whatever the argument of our log is, which is just x. So this is actually a number. It's just, you might not necessarily read it immediately as a number, but e raised to the 13/14 is just a number. And this is the value of x. Now, the question is how many units will be sold, and x was defined as thousands of units. So if we really want to answer this question, we can't forget to multiply by 1,000. And then we would just make sure we round that accordingly. But probably just round to the nearest whole number. So 2,531 should be a suitable answer here. Hopefully you found that helpful. Thank you. Bye.